All right, it is now 9:30 on 9/30/2021. So, yay. Coincidence? Yes. But anyway, let's go ahead and get started with the practice exam simply because I want to make sure I have time to go through reviewing all the problems. All right, normally I like to just be casual about stuff, but we've got work to do today. So, okay, let's take a look at each of these problems. So, first one. Got this doubly linked list. I totally stole this from a Harvard practice final exam, by the way, so, or this problem. So, for each of the following problems, please indicate which node is being referred to by the chain of variables. So, here we've got d.previous.next.previous. That's going to get us to B. And then C will be c.next.previous is also going to be B. In fact, of course, if we've got a .next next to a .prev, we can cancel them out so long as we aren't going out of bounds. So for the next one, right, we see that we've got b.next, that moves it to D, .prev, that moves it to B, .next.prev, they cancel out. In fact, all the answers are B because I'm a jerk like that. I mean, I used to give an exam when I was, before the pandemic, I was given an exam for the freshmen, and it was it was evaluating a bunch of Boolean expressions. They all evaluated a true, which, of course, drove the students nuts, but it made the grading easy. All right, write a sequence of commands that will remove the tail of a doubly linked list. Okay, the sequence of commands that would remove the tail of a doubly linked list are as follows. Give me 1 second to pull up the whiteboard. To remove the tail of a doubly linked list, right, we've got, and I'm going to draw this, I'll do this one part and this next part simultaneously. So we've got ourselves, you know, this kind of situation here. Then I'm just going to go ... so we all understand this is the tail over here, right? So what we want to do is that we need to make this guy the tail. So first we should assign this guy to be this last node to be the tail. That's the first step into removing the tail. So so we need to make tail refer to a new node. So what should that be? That should be, which node are we referring to? Tail.previous. So we're going to take tail.previous and store it in the memory location of the variable called tail. Effectively, what we've got now is a variable called tail that's storing the memory location of that guy. Okay? Next, what do we need to do? We need to make sure that this actually gets hit by the garbage collector. So what we're going to do is we're going to just simply say tail.next is equal to null. Now, by making sure that this is pointing to null, nothing is going to point to this node now, even though it is pointing to something. But nothing's pointing to it, which means that it will eventually get evaluated by the garbage collector, and the garbage collector is going to go nom, 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 I believe the parlance is. So that will delete it. Okay, next problem. And I'm going through these first ones because it is the coding problems that are more important. All right, write a sequence of commands that will add a new item to index 0 of a doubly linked list. And again, for the stuff that you're drawing, you can bring paper or grab printer paper from the lab and just turn it into your TA if you have to, right? Make it their problem. Or you can ask the TA to make sure that you can take a picture of your code so you can upload it. Hopefully you got the permissions and requirements of the exam. Basically, I hope I've laid out very clearly what I consider to be okay computer use versus not okay computer use. But in general, if it's like notes and stuff that you pre-brought to the exam and aren't like having to search for, it's okay, right? If you happen to have come up with a practice answer, practice question on your own, and it happens to be very useful, go ahead and copy it, right? So write a sequence of commands that will add a new item to index 0 of a doubly linked list. So that one. Okay. Nice infinite space whiteboards. Let's use a different colored pen. Yes. Okay. So we've got here our very, galaxy colored linked list with dots. We've got ourselves our head over here. Pointing to this node. This is our head. So we want to add a new node to index 0, which means adding a new node to head. So what I'm going to do, let's assume that our first this node is going to be equal to is called adding. So let's see what add a new item. So we've got this new item. So what we want to do is say, I guess, and just briefly, node adding is equal to new node, item, and we can put in the generics, but I'm not going to do so because it's just going to get even messier with my handwriting. So this is our node adding. We're going to now need to attach that. Then the first thing we need to do is that when we're adding a node is that we attach the new node as best we can. So here, what we're going to have to do is draw this arrow. So what is that? That's adding's dot next, storing some variable. It's storing the variable that is head. So adding dot next equals head. And now what we need to do is that, because it's this is a doubly linked list, isn't it? Yep. So we're also going to want to attach it the other way, which is saying that head dot previous is equal to adding. And don't worry, I'm recording all this, and I'll upload it basically as soon as class is done. Okay, so that will draw this arrow. And then finally, what we want to do is we want to say adding points, sorry, not adding. This node is always going to be adding. What have I done? Oh, wait, I can just press Control-Z. Isn't that brilliant? The benefits of drawing on a computer. Next thing we're going to want to do is say this is no longer head, this is head. Head is equal to adding. Okay. There might be a few other ways to do this, and a couple ways. There's a bit more versatility in how you do this when it's a doubly linked list. Okay. When it's singly linked, you got to be there's generally only one way to attach nodes and stuff. When working with doubly linked, it can be a bit more of a mess. Okay. Next questions. Okay. So here we're going to start getting into actual coding now, which is the fun bit, right? And the part you're most concerned about, which you should be because it's got more of the points. So the drawing questions will be a bit more involved than what was here on the exam, but the coding questions on the exam should be there's much less of them, and it should be easier, and it's a bit more, and you'll have some insights, hopefully. So suppose we have a list of integers. Write a method that finds the minimum and the maximum values stored in the list and returns their sum, regardless of the implementation of the list. So that means that basically we can't assume that this is a linked list or an array list. Now, why did I say that? It has to do with the next part, which is what is the time complexity of this algorithm. Yes?
Does an array list have an iterator too?
Yes, any list has an iterator. But both lists have the get method, so, And I'll talk about that. So what we can do here is that we've got a minimum and a maximum. We want to return the sum of both, so sum of min plus max. Okay. So and if I do, so I'm going to do this because the way I like to do these things when I'm iterating through stuff, which is for each integer integer x in list. I like to try to remember to use i's for my indices. And then what I'll do is I'll just simply say, hey, if x is smaller than the smallest number, if x is smaller than the smallest number we've seen so far, then guess what? X is the new minimum. And then finally, if x is bigger than the biggest number I've seen so far. I could do this as two separate loops, but I don't need to. If x is bigger than max, then max is going to store that value now. Okay, and it's fairly straightforward with regards to that. Now, the only thing you may have wondered is, like, why is minimum equal to maximum value? That's so that the first item I see is always going to be smaller than anything else in it. The other alternative, if I was writing this program, is I could have done list.get, 0 to get the first item in the list, but I didn't want to remind you that get was a thing. I didn't want to pre-prime you to using get, because this way we can do it without get. Now, yes?
So you can't use a regular for loop?
I could. I didn't want to pre-prime you, though. I didn't want to make you think, get. Let's write a for loop that does it this way instead, right? And so the other way to do it was for I in I is less than or equal to, let's see, I is less than or equal to list.size. Yes?
For the exam, will we be allowed to use the official documentation?
Yes. If it exists in Java, you can use it. Oh, like can you look at the doc pages? Yeah, I suppose that's fine.
Okay.
List.I is equal to I is less than list.size. I mean, if you're using IntelliJ, by the way, you can just simply control and click on the class name, and it brings up the documentation mixed with the code, which is useful. So anyway, what we can do then is int x is equal to list.get I, and then we can just do everything else that we had done earlier, right? The same kind of comparison. Now, either way works. It impacts it impacts, though, kind of different things for the next question. So when we write this way, so if we write it this way, actually, let's go over this way first. It actually depends. The runtime of it depends on whether whether the list we're passing in is a linked list or an array list. Because the get method in an array list, so these are all constant time operations, right? So in an array list, this is a constant time operation, so we've got n constant time operations. But in a linked list, the get method is an O of n operation, a linear time operation. So you've got n O of n operations, which means it would be n squared. So depending on what gets passed in, it matters. I'm not going to be too harsh in judging it, though, for that case. But if you want to be always correct and say it's always O of n, the iterator will keep track of where you are, so it'll be O of n. In fact, extra credit is kind of like taking into account all the different kind of edge cases and variations on how it would work. Okay, let's move on to the next one, since we've got that. Suppose you have some list of strings. Write a method called reverse words that returns a new string with all the strings reversed. So, couple of things here. Some people were asking me about the runtime. What exactly is n? There's two ways to interpret that. Always feel free to write down your interpretation. That's how you can justify what your answer is and how I can know how you got to a specific answer you wrote down. But here, both interpretations lead you to the same conclusion, or both valid ones. First off, you just assume, okay, I've got n strings, each of which has the same average number of characters, right, which is going to be constant. So if I double the size of the list, I'm going to double the number of, the average length of all these characters. Sorry, not double the average length. They're all going to still be the same average number of characters. All I'm doubling is the number of words. So it takes twice as long to do. And then if you're saying n is the number of characters, well, in that case, adding more words, eventually you'll double the number of characters. So it ends up being that we can write this in linear time. Now here, though, although yes, because we aren't setting. If we were replacing, it could be a bit trickier. But here, because we are returning a new list with all the strings reversed, it's not going to be so bad. We can create an array list or a linked list as our output list. It doesn't really matter. Because adding to the end of either is a constant time. We can assume that's a constant time operation. Yes, we have worst case scenario for a single operation, doubling the size of an array list it takes O of n, but that happens very rarely. So we can average it out to a constant time operation to adding to the end of a linked list. Or sorry, to an array list. So let's go ahead and create our list. I'll just simply say list of string list is equal to new array list. And if I really wanted to make sure I didn't have to double the number of operations, by the way, if I was worried about like the runtime that would happen if, because I'd keep having to double an array list, well, I know that the size of this list is going to be equal to, the size of my new list is going to be equal to the size of my old list. So if you put in a parameter over here for your array list, it should, variable list might, yes. Return list, I double named. So if you press in the number over here, this will actually set your initial, normally the initial size of the array is set to 10. The underlying array is set to 10. This sets it to whatever list.size is. So you set up with a capacity that's equal to the size of it sets up with something of the capacity that you want. So you can have very discrete control with array lists, which is pretty cool. And now let's go ahead and write return list, just so we don't forget about it. Yes?
Does that prevent the array list always having to double in size?
Yes, it prevents it from always having to double. Of course, if I add one more past the capacity, it will double. But this just simply sets the initial size to something different.
Okay.
So if I pass in 2,000 words, my initial array will be 2,000, so I don't have to bother doubling until I can hold them all, right?
And that would be constant time.
This would be this is a linear time operation because you have to you have to create n spaces, but
Okay.
you're not doing it in a loop, so, and it's pretty much impossible to do this in constant time, so it's not going to hurt you. All right, so next thing we need to actually go through, so, and again, I'm going to use a for each loop. So for string word in word, so string word in list. What I'll do is, so I'm going to be a bit cheeky over here. So first off, I need to reverse the word. So string reversed is equal to blah blah. So I'll leave actually reversing it first for a second. I'm going to just move ahead. So once I've reversed it, I want to remember that I need to add it to the return list. So return list dot add the reversed word. So now the question is, how do I reverse the word? Right, in Python, that's actually pretty easy. I would just do, but word is, reversed is equal to, and then I can use this to reverse a word, which is word, : -1, which would reverse it. Because Python got these awesome abilities to do slices like that, but we're not working in Python here. And Java doesn't know that slice notation exists like that. So how else can I do this? There's no reverse string there. I could go manually through like this, then go, okay, and I'll use another so I could go and get every character and then add it. Or similarly, I could do for car C in, and I can't say word. That doesn't work like that. But I can say word dot to character array, oddly enough, and use a for loop like that. And so that will iterate through every single character. And I can then do reversed is equal to reversed. And this is just skipping a step for doing the get character at, or car at I. And then reversed, and to reverse it, rather than adding it to the end, I just add it to the front. Does that make sense? So I keep adding it to the front, so I would add O to the front, then, let's see, O, and then L. No, I'm going first. So it would be H, then E in the front, then L in the front, then L in the front, then O in the front. So it would be O, L, L, E, H. So that's one way to do it. But Professor Rosen, what about just an easy, painless way to do this without, having to manually do this? I know how to write a for loop and do things in reverse. I want my life to be easy, for God's sake. Okay, fine. In that case, I'll use I'll do new string builder. I'll do it in one line too, because just to be annoying. I think string builder is an older method. I think it's over. I can't remember what it's been being replaced by, but it would work the same way. String builder is used for concatenating things because concatenating things is actually a very expensive operation. So string builder is used to when you want to concatenate things, but also it's useful for doing other operations like reverse. So string builder, that will take in things and then you can add to it, and then I can reverse it because of course it can, because that's built into string builder for some reason, but not string. And then, well, I can't set it like that because I have to convert it to a string, so I say toString. And there we go. And so that's how I do it in 2 lines. Or that's how I reverse it in 1 line and then add it to there in another. You know, that's my secret ninjutsu, I guess, for that one. Regardless, it takes however many of it takes. This step takes, you know, we have so many words, and it takes C amount of steps, where C is the number of characters for. So, you know, each character is effectively touched once, possibly or twice if you want to say, okay, we've got to reverse it, we move it into here, and then adding it involves adding that word. So, I mean, but suffice to say, it's a linear operation. Okay, or rather, this for loop is a linear operation. Again, because we're using an iterator, and again, it would be the answer if you're using the get method. Then with a linked list, it would actually take longer because of n for the gets. All right, linked list. So this is for deleting the list. So first off, if this is a this method, so let me go ahead and make a linked list exam questions here. So I really don't need much for the linked list exam for this to actually just code stuff and make it syntactically complete. I just need the minimal set of stuff, which is say that I have a node. So first off, I'm going to go ahead and I will use ease just because. We need to define a node class, private static class node e contains, and it contains thing, let's see, it has a node e next. Depending on the problem, it might have a node e previous. For right now, I'll assume that we have to deal with previously, and then an e item. And then I suppose I'll just write the constructor as well, which is that just because I might need it. So public node e item is equal to e, or this dot item is equal to item. There we go. Boom. And now, a second. And now what we've got here is we've got, I missed the message that somebody wanted to zoom in. Oh well, I'll upload the recording ASAP. Okay, so we've got ourselves our constructor, and we need a node e head, node e tail, and this should serve us well for the next couple of questions. And a node, sorry, an int size. That's all we really need to get started, just to make sure that our code will compile, although we might not be able to test it. So let's see. We want delete list, which will delete the remove all the items in the list, which will make it empty. A couple of different ways to do this. Actually, a lot of different ways to do this. First off, if we're just dealing with a singly linked list, we can deal this with this in O of n time, but we're not dealing with a singly linked list time, which is that we can do this. We can just simply set head is equal to null, tail is equal to null, and then that will garbage collect the head which will then garbage collect, and since nothing will point to head.next, that'll garbage collect that, and since nothing is going to point to the one after that, it'll garbage collect that, and so on and so forth. Basically, everybody with nothing pointing to the first node, that will get eaten, which will cause the next node to get eaten. It's just kind of a domino effect. And then we set the size equal to 0. But let's say that since this is a doubly linked list. Well, here's the really dumb, easy way if we're dealing with a doubly linked list, which is we can just simply say, well, there's nothing stopping us from doing this, right? Because there's a remove method that we've written that linked lists have. I could just simply say, while list.size is greater than 0, or sorry, while this.size is greater than 0. While this.size is greater than 0, this.remove index 0, so while we still have stuff in the list, remove, just remove that thing. So that's one way. But what if this was an interview problem and they were saying, well, we don't want you to use remove, what if you have to do it manually? Okay? Fair enough, right? So the point being is that there's a lot of ways to do this. There's a lot of ways to skin a cat. Although I say that, and A, you shouldn't do that, and B, nobody ever tells me any of the other ways. So, So what I would do here is I would say, well, head is not equal to null. What should I do? I would say, basically, head is equal to head.next to advance head by 1. But here, if in a doubly linked list, just by advancing the head, I'd still get this kind of situation going on, where this guy is going to be kept alive because head.previous is pointing to him. So we got to ixnay that. So now the current head, we just simply say head.previous is equal to null, which will kill that. We don't need to bother killing this because eventually that will get garbage collected. I mean, we could if we really wanted to, in which case we'd put that above and say head dot previous dot next is equal to null if we really wanted to do that. And then we could do size minus minus here if we wanted to, but I'll leave that to the end. And eventually head will advance to being null, in which case we'll stop and we'll just simply say tail is equal to null, so that will get removed, and then size is equal to 0. And that will take linear time. The other ways would take, the only way to, the singly linked list is going to take constant, but these ways the other ways I've shown take linear. Okay, next problem, because that one was only 3 points and not particularly interesting. All right, write an instant method called count. Count iterates over the linked list and returns the number of items that occurs in the list. So you can use head, tail, and this. And let's go ahead and just write this in linear time. And if we're working a linked list. If we're trying to write this in linear time, then we can't use the get method, right? So here, what am I going to do? I will just simply say node e, yes.
So the garbage collector always runs in constant time?
The garbage collector removing an item is not something we have to consider.
Okay.
Yeah.
I did it that way with like long head is not equal to null, and I get like a null pointer exception when I run that. And I had to do it when head is not equal to tail.
When head is not equal to tail? Let's see, when head is equal to tail. So what if head is equal to tail? Oh yeah, if head is not equal to null. Aha! Right, good point. So we want to do head.next is not equal to null. And then maybe we have a couple of other operations to do there, but
So why was that even a null pointer exception?
because we'd move on, because if head wasn't null, we'd move on, and then head would become null. And so that's the issue that would happen there. Head would become null, and then we'd be trying to do head dot net is equal to head dot next and get an null pointer exception. What we could do over here, let's see. Even better. Is that we could do this. Which is that we do the operation, this advancement operation at the end. Remove the thing I'm pointing to at the end, then advance. So for the first item, this would just simply set head.previous is equal to null, which would set null equal to null, and then we'd advance head. There we go. Yes?
If you did just like that head equals null, tail equals null, would it not be, would the middle ones not be garbage collected even though you can't get to them?
I don't believe so, because I think they're each keeping each other alive there by each pointing to each other.
So even though you can't access them, they're not gone?
Yeah, I think that's a memory leak. I believe. I'd have to look that up. And because I'm not sure, I'm going to make sure to remove them manually.
Okay.
So, node E current is equal to head. And so what do we do here? So we're going to say, well, head is not equal to null. Yeah, sorry. Well, current is not equal to null. Right. And then at the end, we will advance current. Current is equal to current dot next. There we go. Okay, so what are we going to do here? We're going to move. So what we want to do is we want to check the current node we're on and see if that contains the item. If current dot item dot equals the item I'm looking for. Again, this one's a fairly straightforward one. Int count is equal to 0, or int. Let's not double name our things. So int sightings is equal to 0. If item is equal to, if item current dot item is equal to the item I'm looking for, sightings plus plus, and then we just move forward and then return sightings. And fortunately, with this one, it works the same. You know, we don't need to worry about dot next or we don't have to worry about dot previously. We don't have to, because if this kind of thing works on a single linked list, it will work on a doubly linked list if we're not going back. You know, since we don't have to concern ourselves with going backwards or anything like that. Okay, this was a linear time algorithm because it goes over each node once. Okay. So now let's talk about this method. Write a static method that takes in two sorted linked lists of integers and merges them into one sorted linked list and returns it. Since the static method outside, you cannot access the nodes. You are allowed to access and remove items from list A and list B. So here what I'm going to do is I'm going to go ahead, and since it's static, I'll work on outside this class so I don't accidentally access the nodes. Okay? And I'll just go ahead and use standard linked list classes over here. I mean, they're lists, but I mean, they're going to be, but I mean, I'm being told they're linked lists, so I could change this if I wanted to, but I also want it to fit. Let's go ahead. So since we know they're linked lists, I should technically write them as linked lists, but on paper, I had only so much space. So you've got list A and list B. They're both linked lists. We need to return a new list, which I'm just going to call output. So linked list E, oh sorry, it's an integer. So linked list of integer output, assuming I can spell output, which apparently is difficult. New linked list, boom. So we've got ourselves our output, and then to make sure it always compiles, return. That's one of the things I do when I'm writing code. I always make sure it compiles. I'm never going to be in non-compiling state, because otherwise any errors I make in the future could be overshadowed by my current errors. So that's why I do this I essentially get the slices of the bread for my code sandwich over here, for want of a better metaphor. Okay. So here's the thing about these numbers, okay? What I've got is if I've got a bunch of, I've got two lists, 1, 4, 7, 8, and I've got 2, 3, 9, and 12, okay? How can I merge them into one list? Well, the cool thing about this is that if I look at the front two items, right, if I look at the front two items of each of these lists, I can make a pretty cool comparison, which is that whichever item is smaller, I know that's going to be the smallest item overall, because if 1 is smaller than 2, because 2 is the smallest item in list B, it's going to be smaller than all the items in list B, because it's smaller than the smallest item in there. So with 1, so okay. And then here's the trick, which is that I'm going to just simply remove it and move it into my output. And now I can continue to keep doing this check. So 2 versus 4, which is smaller? Well, 2 is, and because 2 is smaller than the smallest item in this other list, I know it's smaller than all the other items. So I don't have to bother checking against them. I just have to check against the first one. So 2 is smaller, so I'll add that to here. Then 3 is smaller than 4, so I'll add it. 4 is smaller than 9. 7 is smaller than 9. And then 8 is smaller than 9. And then we're left in an interesting situation where we have 2 left over versus none, and obviously I don't want to compare nulls. So, however, I know that these two items are sorted. They're in the right order. And all I'd have to do is that basically I just have to attach these to the end of the list and be in order, because they're bigger than everything else. So basically I'm going to do this comparing the front process until everything is empty. So, and then I'll tackle that from there. Okay? So, one while loop here, just with 2 conditions. While list A dot size, and if they don't want you to remove any items from here, if you're allowed to use auxiliary space, then just simply create a copy of list A and a copy of list B, right? Which is a bit too, which adds in a couple more lines. If you're not even allowed to do that, then there's really no way to do this in linear time. But and that's why I'm using linked lists, because the remove 0 method will run in constant time. So while list.size, yep, because this is greater than 0, and list.b, yes.
Couldn't you possibly use an iterator in that case?
Yeah, I suppose we could use an iterator. That's correct. You could use an iterator, although with an array, then that would work for a linked list. But with an array list, remember, removing is going to be a pain in the butt. But yes, iterator would do it. Just be a bit weird. No, you just have a 2. You'd have 2. You'd have to, yeah, you could do it with an iterator, or 2 iterators rather, 1 over. Okay, but I'm going to just do it manually here. So while one of these is not empty, while both of these are not empty, what am I going to do? I'm going to basically ask myself one question. If list A dot get 0 is greater than list B. Actually, I'll make that less than. That makes a bit more sense. Get 0. And we can assume no duplicates, but even if there are duplicates, the way we're coding it is that it will assume a duplicate is greater than. Okay? If I wanted to make sure, if duplicates were less than, I could just do that, less than or equal to that. So if list.a is less than or equal to what's on list if the left side is less than or equal to what's on the right side, then the left side is the smallest number. So we would do output dot add list A dot remove 0. So we remove the first item and add it to the end of the output. And then otherwise, we just if the thing on the left isn't smaller, then the thing on the right must be smaller. So we just simply copy what we have, paste, and just flip that A to B. And this will run until one of them is empty. Fairly straightforward. Okay, now we have a bit of a trick though, because we just emptied out the when we're out of this, we've emptied out one of the lists. Guaranteed, if we've emptied out one, then the other one has to have items in it, because if the other one didn't have items in it, we would have stopped earlier. Okay, which one? Well, we could do an if statement like that, but honestly, I'm just going to be lazy. I'm going to be very lazy. Output dot add all. Very cool method, add all, by the way. Guess if you haven't seen it before, it's built into your collection to your collections, and it does exactly what you'd think it would do, which is that it adds everything. And yes, that would be a linear time operation. You know, you're essentially adding every item individually. Unless they're, for linked lists, they have a clever way of doing it, which would be constant time, but whatever. That's either here nor there. So I'm going to add all list A and output add all list B. And this is, and what I mean here is I don't really care which one is empty, because I've emptied out list A or list B. One of them is empty. So that add all method would be basically essentially the list equivalent of adding 0 to a number, right? Not going to do anything. So, yes?
That's a question. So, like, when did you need to use an iterator, like you mentioned earlier, for the iterator? Because the assignment, you kind of gave that to us already.
So his suggestion to use an iterator was if we couldn't use the remove method, and we couldn't use any auxiliary space, and you still wanted to do it in linear time. The iterator would be the only way to do that.
Do we need to know that for?
No. Okay. I do like working with sorted linked lists. So again, this is a linear time operation, which is what I was trying to do, because again, so now what is the time complexity of the algorithm? That actually depends on assumptions again. If we assume list A and list B are the same size, both n, then it would take O of n time. However, if list A and list B are different sizes, then the amount of runtime, if one is much small, if list A is much, much bigger than list B, right, but not necessarily like an insignificant, then we should need to take that into account, or we don't know which one it is. So we would say, they like to write n plus m, and I hate that because those n and m sounds like M&M, and that makes me think of candy, which is not great, because I need to lose weight after this pandemic, So, but also it's just like abstract, but it would be, in this case, I would say size of, I would just write, because I'm not a mathematician and I'm allowed to use more than one variable, size of list A plus size of list B, if they're not the same size, right? Does that make sense to everybody? Because we've got essentially n for one, an n for one, an n for another. We don't know necessarily what they are. Another way we could write that would be O of A plus B, or O of n plus m. They all mean the same thing, right? We have two different lists of two different sizes. We don't know which one is bigger, and we don't know what magnitude, but we're not going to assume, right? Now it's n plus m because not every item is getting compared against every other item. Each item in each list is only getting touched once, right? If we were like basically checking, if we were to do an operation where we are checking for which items in list A also appear in list B, that would be an O of A times B, because we'd be checking. Okay, we'd check the first item in list A and check it against all the items in list B, then check the second item in list A and check it against all the others. So that's when we'd multiply. Basically, that you'd be, and if they were the same size, you'd say that was n squared. So A plus B is basically used plus when it would be like a linear equivalent, and multiply when it would be a quadratic equivalent. So. hitting. Okay. Okay. Okay, I'm going to skip this one for right now, the reverse one. Because I can do it very quickly. This one's really dumb because it's actually a classic interview question. Because they'll say, okay, do this. Okay, you've done this, but now try it, and then eventually, but try it with this restriction. And eventually, the restriction is singly linked list, no and no auxiliary data structure, which is a pain in the butt. But again, I really just like to use the add and remove method to get around these things. So if I've got a double, and it's much easier if it's doubly linked list. Going through this is a trial in itself, and I highly recommend you look up how to reverse a singly linked list, just for kind of practice sakes and trying to understand that. It's a really good exercise. But here, I'll go ahead and put it in this. Public void reverse, which what would do is in a linked list is that it would have to reverse everything in a linked list. So in that case, what I would do, I'd be really dumb, and I'd say, hey, make me a temporary linked list. Okay, if that makes sense. Is equal to new linked list. And it imported the other linked list, because this is the linked list exam questions class. Whatever. Point being is what I'd do is I'd say, while this dot size is, I like to do, while this dot size is greater than 0, then I'm just going to remove an item, right, from this list. So this dot remove, which I haven't written for this, but you get the point. This dot remove 0. And that will be added to temp. Okay? Temp dot add. Okay? So I've emptied out my original list, and I've duplicated in the other one. Okay? And then what I'm going to do over here is that to reverse the list, I will just simply say while temp dot size is greater than 0, temp dot remove 0, right? Remove it again, and then this dot add, except rather than adding it to the end, because that would get me back to where I started, I would do 0, which would add it to the head. And so that's just like with the reversing of our, like the reverse string, reverse all the strings in a list method we saw earlier in the practice exam, whereby adding something to, constantly adding to the front will effectively reverse it. So that's a way. There's a lot of different ways to do this. Some are messy, some are not so messy. Just, there's a lot of different ways to do it. And because, again, the bulk of what I want to practice today is this problem over here. That's why I've been moving quickly, because I keep forgetting, oh, right, I've got tons of time. All right. So suppose we have a new type of linked list, the sorted linked list. So sorted linked list. Over here, dealt with sorted linked list in this question. This is what we might call in the game a hint about what the exam might cover stuff with the sorted linked lists, right? Obviously, I won't ask you to write an add method because we're doing that here. What would a remove method look like? Maybe think about that. Okay? So, suppose we had a new type of linked list called sorted linked list, which is a linked list, but it keeps all the items in the list sorted. As a result, when we add it, we don't need an index because indexes are meaningless for this operation in the sense that, yes, each item does have an index, but I can't just add an item anywhere. Where it goes is determined by its value. So your task is to now complete the add method for a sorted linked list shown below. This method inserts a new item into a sorted linked list in such a way that it remains sorted. For example, the list is 1, 2, 5. We add 4. We're going to get 1, 2, 4, 5. So we can add a singly or doubly linked list. I'm going to use singly. For God's sake, I'm going to use singly. Okay. You can use greater than, less than, or equal to compare items, but if you remember how to use compare to, you'll do so for extra credit. I'm going to use compare to so I can do this using ease. I can't call this method because, again, it doesn't really exist here, and I also want you to avoid using that method. You cannot use the get node because that's although you could rewrite it, because if you really wanted to use it, you could rewrite it without actually calling it get node, right? But the reason I'm saying it is that I don't want you to, I don't want you to use it because it's a linear time operation, and your solution must run in linear time, which means that you can only really use the get node method once. And if you're going to use the get node method, you probably have to do it multiple times. So linear time. So on the exam, the problem might be worth 20, 25 points. The linear restriction is something like that. If you can't solve it in linear time, that's like a 5-point penalty. Okay, so it's not going to be instantly wrong. It's going to be well, that's the price I pay if I can't do it this way. Okay, so because I do want to make sure that you understand it, but sometimes you can't get to the right runtime. Okay, so public void add an item. So first, I'm going to create a sorted linked list class. Let me go ahead and comment out this nonsense over here. Okay. Similarly, I'm going to just copy this because I need this bit over here, and then I'm going to need to do some other nonsense. So sorted linked list. Okay, it's a sorted linked list of e's, and because we want to be using the compare to method, I'm going to say extends comparable, which enforces that all the e's in here are going to be comparable. What does comparable mean? That means that there's an ordering for them. That makes sense. Okay, and that means they only have one method, which is the compare to method, which I'll go over when we use it. Okay, next, let's go ahead and create our node class, and which should be node, and our head and tail, which should be no different than anything else. Notice that it wanted to say, oh, obviously you want to use this class there. And I'm like, no, I want to make my own node method. Stop trying to help me. Don't help me. I got it myself. Okay, so there, we've got a node head, we've got a node tail. We're going to go ahead and move this to where I like it to be. And now we are going to, we're dealing with the same standard kind of stuff we have. And finally, because we have, I don't think we need anything else. Okay, public. And here I'll try to take this one slower because there is a lot of, I know I've been going at a blazing fast speed. Public void. Am I running out of time?
Sorry.
No, it's fine. We've always got, if we try to keep our attention focused on stuff, we are just all going to go crazy, So no worries. All right. So public void add item. So we're going to add this item. Now, okay, when you don't know where to go with this kind of thing, when you're adding or removing, always fall back to thinking, what are the base cases in the standard add and remove? Because the base cases exist to keep us from in trouble, to keep us out of trouble. What is the trouble we have in linked lists? Going out of bounds and destroying the list. The destroying out of bounds. So the going out of bounds is just generally when we are at the head and tail and we modify that and we don't address that properly. So that's what leads to the null pointer exceptions. And that can be directly going out of bounds because of the indexes or because we're messing with the head and tail all wrong. And we don't realize we're doing that. The destroying the list happens through bad programming, so we just avoid that by being good programmers, right? But in all seriousness, those two kind of methods are tied into each other. So let's just think about our 5 cases. So first off, the first case in adding is if the provided index is out of bounds. This does not apply here, right? The first of our 5 cases, because we don't have a provided index. So we don't have to worry about an index out of bounds exception. That's just not a possibility here. All right. So is my other one? What if this is the very first item I'm adding to an empty list? Okay, that's easy enough. And let's go ahead and just simply say I'll just create the standard public int size, which we call size for some reason rather than get size. Really prefer, again, the Python way of just simply calling it, of just having a len function for everything. Okay, return size. And I'm sure you've all heard my mini rant about size and len. Yes, no? Okay. So what we've got here, okay, if this dot size is, okay. Also, I'm just going to, before I forget it, size plus plus at the end, because no matter what, because there's no index out of bound thing, it's going to increment the size anyway. So this dot size is equal to 0, then it's the only item in the list, so yeah, let's go ahead and make our node. Node E is adding is equal to item, new node E, I need that, item, right? Okay, and now we would just simply say that head is equal to adding, tail is equal to adding, and then, yeah, that's all we need to do. We don't need to make it circular or any nonsense like that. Yes?
So why can't we just do this dot size? Why do we have to write a function to return size?
Just trying to make it match, that's all. I could do it.
Okay, but right, is that because the int size is not private, or if it was private, it would still work?
It's private, but because I'm inside this class, it would still work.
Okay.
It's just convention. I mean, honestly, it's fine.
Okay, because I was I wasn't sure which one to use or why, so.
Again, this is why I like the length function, because in Python, we don't have to worry about these kind of silly questions here. Okay. That being said, Java is a great language when compared, especially with using like other languages. So other conditions. What we really care about that can mess us up is we don't like properly keep track of the head or tail. So the head and the tail is going to change. So the head and tail changing are two possibilities here. Now in this case, rather than adding to index 0 or index size, it's going to be different, which is if the item I'm adding is smaller than everything else, that's going to be adding a new head. And if the item I'm adding is bigger than everything else, that's going to create a new tail. So, okay. So if item dot, so how do I know if the item is smaller than everything else? Well, again, I just have to compare it to the smallest item in the list. Now the way I do this is I use compare to. Compare to head.item. Okay? If item.compare to head.item, and then the way I check this is I say less than 0. So the way compare to works, for those of you who missed it or can't remember, compare to works is that you've got two sides, A and B. Okay? If A is less than B, or if A comes before B, either way is a proper interpretation of it, then you're going to get a negative number. If A is greater than B, you're going to get a positive number. And if they're equal, you're going to get 0. So here, I'm saying if item.compare to the head of the list gives me a negative number, that means that item is going to be smaller than that. With integers, that's going to be, always -1, but it can be any negative number. Like, for instance, if we do letters, we can get like, if we do strings, we can get like alphabetical distance, which is interesting. But it works here. And this is essentially the equivalent of me this is the equivalent of me asking if item is less than head.item, if that makes sense. Right? So if adding is going to be smaller, so if the item I'm adding is smaller than everything else in the list, then what I'm going to do is I'm going to attach adding. So adding dot next is equal to head, adding. Adding dot next is equal to head, and then head is equal to adding. These conditions over here are the pretty painless conditions to do because just these are constant time operations. Just simply attach it and then update. Yes?
Is using comparables better than doing the
I mean, it will
operators?
work on stuff other than integers, which is cool.
Oh, okay.
So this will work on stuff other than integers. If you're just using if you're assuming that it's only made of integers, then you are allowed to use less than, greater than, you know. Actually, to make this a bit easier on myself, I think I'll say that if it's less than or equal to 0, so that if it's equal, that's just, you know, if it's equal to the head, I'm going to put it there. It's just either, it will work either way with the way I'm thinking about it in my head, but, you know, else if, and now item dot compare to, I'll go ahead and move this up so you don't have to stretch so far. So item dot compare to tail dot item if that's greater than 0. So if item is greater than the last item in the list, if it's bigger than everything else, if it's bigger than the last item in the list, it's the biggest item, so it's going to get added to the tail. So that in that case, I would say tail dot next. Don't point at null anymore. I need you to point to adding. And I would say tail is equal to adding. So attach the last node to the new last node, and now update the list to say what the last node is. And again, I don't have to write size plus plus anywhere for that, because I just do that here. And now we're in every other case. Well, crap, right? Okay. So the way this one works is a bit of a nuisance, but I think you'll see. So if I've got like 7, 9, 12, 15, and I'm trying to add 10, okay? Dot, dot, dot over here, and this is the head, right? I don't need to say, hey, do I need to put 10 before 7 anymore, because I know I don't. I've just checked that. So what I'm going to do is I'm going to start like over here as current. I'm going to say, hey, does this fit between current and current.next? Right? Does this fit between 7 and 9? And the way I would know that is I just have to compare it to 9. Is 10 less than 9? No, it's not. Okay? And then I'll move on to the next, and then I'll make that one current. And I'll say, hey, is 10 less than 12? Yes, it is, so I'm going to put 10 in here in between those two. Okay, so node E current is equal to head while, and I think I want to make sure while current dot next is not equal to null. Now, why is that? Because that means until we hit until current, basically, if current.next is equal to null, we're at the tail, and we don't need to check after the tail because we've done so already. So what I'm going to do now, I'm going to remember to advance current. Current is equal to current.next. I might have to do a break statement somewhere. I don't remember, but we'll see. There's different ways to do this. So, and a break statement does seem to be straightforward to get out of here. So while current.next is not equal to null, what I'm going to do is I will compare item. If item dot compare to current dot next dot item. Is less than 0. Sorry, yep. So here what I'm doing is I'm asking, hey, does this item fit between, in this case, right here, I'd be saying, if this is current, right? This would be current.next. And what I'm saying is, hey, is 10 less than current.next's item? It is not, so that if statement will not take effect. But for the next time, I'd go forward and I'd say, and I'd ask, okay, this is current. Is it less than current.next.item? Yes, it is. So what do I want to do? I'd want to put my 10 in between those two things. Again, drawing this out really helps. So here's my 10, which is adding. The first thing I'd want to do is attach this guy. Yes.
Shouldn't it be less than or equal to, in case like those last two are the same?
I mean, yeah, it could be. It will still work if it's not.
But then it would be at the tail, and then you would have to try and change the shape of the tail.
Oh, you're right with that. Well, we've always checked the tail.
Right, so when it break,
We could avoid that we could also avoid that by doing that over here. If that makes sense. So if it's greater than or equal to the tail, then it would be bigger than tail, so we could add to the end. Make sense? So now we don't have to worry about that case. It's a good point, though. Or we could just do it over here, which does make it more consistent with the code we currently have. And it would stop it sooner, which is and to be more efficient. So that good point there. So item.compare to current.next.item. Okay. Okay, so yes, where was I? Yes, first thing I'd want to do is take this node, which is adding, and attach it. So I'd say adding.next is equal to current.next. Attach it like that, right? And then I'd have to take this and move that over there, which would be current.next is equal to adding, which again points current.next and stores the memory location of adding inside current.next, so it will point to this one. So that first thing we did, we attached it, and then we moved this pointer over here and moved it to to point there. Okay. Now this point we could just keep it going on and it would not do anything else, but that's okay. Actually, no, if we didn't stop it here, it might, if we didn't stop it here, we'd have an issue. Because current.next would now be, we'd add an infinite number of items here. Or self-referentials. It would be a pain. So what we're going to do now is that if that condition is true, and we've added our item, I'm going to just put in break. I'm not going to return because I wouldn't increment then. But break would break out of the while loop over here, so that'd be fine. So let's go ahead and shrink this size down, or shrink this down a bit. And yeah, it's a lot of writing for this one, but this is the closest to what's actually going to be on the exam. So again, on the exam, what you're going to want to do is consider your cases. Is the head going to change? Is the tail going to change? Can you write it in such a way that we can avoid changing the head or the tail? Yes.
Why does that while loop keep running? Wouldn't it break at some point?
It would keep running because while current.next is not equal to null, well, what we said is current.next is equal to adding. And then we'd said, so this would be current. The current is equal to current.next. So this would be current now. And then I'd be asking, hey, is the item I'm adding less than this? Yes, it is. So, okay, we're going to we're going to have current, and we're going to point current.next to itself, I believe, and it would just get messy. I don't want to think about how messy it would get. It would obviously be an error. So that's why we're going to break here. Another way to do that is to have a Boolean over here like this, which is simply going to say Boolean is equal to done. Sorry, Boolean done is equal to false. And we can say, well, current .next is not equal to null. And not done. And then rather than setting up break, we can just simply say done is equal to true. But that effectively becomes the same thing. Okay. Now it does run in O of n time because guess what? I'm only checking each number a maximum of one time. Okay. Now, the main issue I see on the exam for similar problems to this is that students will mix and match the item and the node. So they'll say something like item.next, you know, and for some reason that really irks me. So please don't do that, right? You know, you want to make sure you understand the difference between the node and the items in there. Similarly, they might say something like, if you're trying to merge two lists together, they might go list.next is equal to, you know, other list. Don't do that, you know. Or list.next is equal to other list.head. But that doesn't take into account things that you'll have to change, right? And also list.next isn't a thing. You'd have to do list.tail.next, and then you'd have to say is equal to list.head. You know, and then you'd have to adjust the size. So just be mindful of what you're doing. And when in doubt, write pseudocode in a comment to let me know that it's pseudocode and not actual code. And so I can judge it differently than actual code. You know. So, okay, last problem, which I believe I told you would be on the exam. That hasn't changed because I'm a man of my word, or at least I like to say I am. So, okay, so the list can be implemented in a number of ways. Compare and contrast an array list and a linked list. In which situation would you implement one list over another? Okay, so there's three ways we can compare and contrast them. Memory usage, modifying the list, changing the length of the list, so add and removal, and then retrieving values or modifying values within the list, so your get and set. Okay, those are the three basic things. Now, Big O, like cheat sheet, has some answers, but you got to have some context for them in order to be correct. Like for add and remove, it will say constant time, but that's only true if you have a pointer to where you're going. Memory location. Memory usage. So, Arraylist uses an underlying array, which means it's fairly memory efficient in terms of like everything that we use, because arrays are about as efficient for memory collections that we get. Everything in an array, right? When we store an array of objects, technically what we're doing is we're not actually storing an array of objects. What we're storing is basically we're storing some memory locations, right? So the memory location of this item, the memory location of this item. Why am I writing fat? No, that won't work. Fad, beef, OX, A, B, C. So it would store these hexadecimal memory locations. It wouldn't actually store the item itself. So it's fairly straightforward. But with an array list, we can run into an issue of wasting memory, which is that basically, let's say I've got myself in a big fat array, right? And I've added a bunch of items to it, and now I got to add one more. Well, now I got to create something that's twice the length and then copy everything over, right? And then I add one more, and then I add this one more item into it. And then suppose I don't never add any more items in. Right? I've essentially wasting half the space in the array. Yes?
So would that be considered
A linear time, a linear space cost?
Oh, I'm sorry. The question I misread. I thought we were supposed to list like 3 different things.
Yeah.
But
Yeah, I'm just saying for space, how they each use it. So it can waste this memory. Now, there's a way to get around that. That is the trim method, which would basically takes O(n) time. It copies it over, and it copies it over into an array, underlying array where the size and the capacity are equal. That's great if you don't add any more items. Of course, you add any more items and you get into the same problem. You also run into this situation, by the way, if you've got a bunch of items and you start removing a bunch, right? So you have because we don't shrink our capacity, because if we were going to add, we could get into a situation where we could like add an item and it would double, then, we'd double and copy everything over, and then we'd remove an item, and then we'd have to move everything over, and that would just be very costly. There's ways around that, but, just not doing it naively, but that's but we figure that adding, we can waste the space there. So, linked lists waste their space in a different way. So, whereas each thing just simply had a memory location in here, a linked list has each slot for an array list. So, each slot for an array list just simply has a single memory pointer. Each slot in a linked list, each node, has 3. It has one for the item, the memory location of the item, the memory location for the next item, and then if we're doing doubly linked lists, the memory location of the previous item. Now, we're not dealing with any issues where basically we're doubling, where we're doubling the, we're not going to waste any spaces by creating random nodes that don't have anything in it. But we're still using memory in a different way, which is that we've got basically 3 times the overhead cost. Like, if I'm going to compare a linked list to an array list of the same size, where the size is equal to the capacity, the linked list is going to use 3 times the amount of overhead, right? And I say overhead because, like, the underlying objects are probably more expensive than the memory pointers. But it's still a cost to consider if you're trying to be memory efficient as possible. So those are just the considerations to have, that you would have. But with a linked list, you don't have to worry about like the expanding and contracting of the capacities. So that's great. So it really just depends on your preference to those two. But being aware of those different costs matter. All right. So what about get and yes?
Are memory pointers stored in the same locations as the value is?
Now, I mean, in an array, yes, they're stored in the slot, in the index, but that just memory location points to that item, that value.
How about in a linked list?
Same thing. It points to some kind of it points to some kind of ethereal giant thing in memory if it's a big object like a server, or a text file, or a giant string, right? You don't necessarily store, because Java makes it nice for us. These are all references. These are all memory locations to items that are just scattered throughout memory. And we can go to them in constant time because we know where they are. But we can't necessarily go to them, but we don't actually store the item itself in the array, in these arrays. We just store the memory locations. I need to move on because apparently we only have 1 more minute. So, okay. So, very quickly, get and set. Not get and set, add and remove. For a linked list, that is extremely easy. Get and set, add and remove is constant time on the ends of a linked list, the head or the tail. But if you're moving anything in the middle, you have to seek to that location, which takes O(n) time. For an array list, that is the most complicated thing about an array list, where if we are adding and removing from the front, we have to shift everything over. That's linear time. For adding and removing from the middle, again, linear time, because we are shifting half the things over. If we're adding or removing for the end, removing is always constant time. Adding, usually constant time, except when we need to reallocate. So, in which case it would be O of n time. Get and set are simpler. Array lists, get and set are always constant time because we can just seek to a memory location of the array. But in a linked list, you can't. Getting a random index is going to take O of n because you have to do that scavenger hunt. And since get and set simply operate the same exact way, the only difference is that when you set something, you also change it besides returning it. Then that, that's also going to be a linear time operation. So if you want to add and remove, linked list is probably the way to go. If you want to, once your data is set up, and you need to manipulate the indexes a lot, or go to indexes and stuff, you probably want to use an array list. Where linked lists excel are where we have to split up an item. Sorry, when we have to split up a list into multiple lists, into sublists, and then move all the items around inside a list. Linked lists are really good at that. All right, so that's that. I will